This is Science 8, and we're pursuing our inquiry in our education, and we're pressing now towards a curious kind of a threshold. In a 2-year education, the first year was an integral pattern, the way in which nature tends to actually make form, bring things together, the way in which matter holds a relative stability of form. And we saw that even on the level of subatomic particles like the proton, that form holds in this universe for a very long time. And yet there are variations of forms that are so fleeting as to only occur in not just millionths of a second, but billionths of a second. The proton lasts approximately 22 billion times longer than the universe has lasted already. So they're very stable. They don't go away very easily. And yet, the proton, if it were placed in a scale model of an atom, where the atom would be the size of a football field, the proton would be a marble on the 50-yard line. So that most of the atom of any element is space. It only occurs that that space has solidity, has stability, because of a relationship of electrical charge between that proton and the negative charged particle, the electron. And it's because of the stability of that electrical relationship that atoms have form in the first place, and that they have any kind of stability, even to the long-term stability. If you have just a single proton and a single electron, the simplest atom, that's an atom of hydrogen. And that hydrogen seems to be everywhere in the universe that we look. And the first year of our education emphasized how integration, how coming together, how coming into form seems to characterize the normal universe, the normal life that we live. And that in the ecology of the way in which integration occurs in more and more complex ways, that the integral process of nature doesn't stop with existence, doesn't stop with matter, but continues its density, its complexity, its integration, until one of the ultimate forms in the universe is our mind. And that the symbol is an integral form, just like matter, just like existence, only much higher energy, much more complex, capable of a densification that seemed almost impossible to us for matter before we found that there are such things as protons and another form of the proton called the neutron, stripped of their electron shells, and that the protons are packed like eggs contiguous to each other, and that the form of that kind of materia is called a neutron star. And that neutron stars are so thick that a teaspoonful would plummet through to the gravitational center of the Earth from its sheer weight, its density, its laser-like concentration of material form. The mind has a kind of a complexity of form like a neutron star. It has the ability to make integration to a scale of energized complexity that is not seen existentially in nature. And yet the mind is still a part of nature. It's at the far end of a scale of integral complexity. And that integral complexity has a very peculiar quality that we have learned to observe in the exterior world. And that is that when you get to an ultimate limit of form, there is not an ending or a stopping like a box canyon, but that form becomes available for a transformation. That the principle, the old wisdom principle, that in order to transform something, it needs to be brought to its perfection. If it's a liquid or a gas, it has to be brought to a place of full saturation. If you take a tablespoon of ordinary table salt and you dissolve it into a glass of water, you can do that several times, many times. But there'll come a point where the glass of water will not dissolve any more salt. And that liquid then is a saline solution that is saturated. And we know that a saturation at the very cusp, at the very limit of completeness, of fullness, that sometimes if you add one more iota, it precipitates all of the materia that was dissolved out into a crystalline rain, out into a recrystallization. And so this whole process where integration comes to a place of incredible complexity, incredible saturation, the next step beyond that is not an impossibility, but is a transform. And usually what the transform brings out is the essential form of the structure at its most complex. And in our terms, our mind does not come to an end when we bring integration to its fullest, but we experience a transformation also. Just like a neutron star transforms into a black hole, into something which characterized by physics is called a singularity. And there are many books now in the world. The theory of singularities and its applications, the analysis of space-time singularities. And these kinds of studies are all over the shelves of astrophysics and physics and chemistry and molecular biology and everywhere that one would go. And yet 35 years ago, there was hardly anyone who would have talked about singularities, would have talked about black holes, a phrase developed by a Princeton physicist named John Wheeler. He was sitting in his bathtub wondering what happens to a neutron star that gets so much more complex that not even light can escape from it. And he came up with the incredible idea that it became not what some Russian physicists had said, a frozen star, a star so packed, so gravitationally thick that light and magnetic structures lay plastered on the surface of the star and couldn't escape, and that it was like a frozen star. It was a star petrified by complexity. And Wheeler, sitting in his bathtub, saw that this was not right, that this was an image. It was an imagined image. It had a mythic quality to its imagery, and that in fact, in terms of visionary consciousness, what happened was that there was an implosion to a singularity, where all of the materia, all of the matter, all of the nuclear material acted as if it were a single point, as if it were a single thing. And we know now that it doesn't have to reach a neutron star collapsing into a black hole, but that material, almost any kind of material, but especially some of the right kinds of material brought to near absolute zero, absolute cold, brought to where there's no thermal activity whatsoever, that especially in terms of like the element helium, if you bring helium to almost absolute zero, within a few smidgens of absolute zero, all of the individual atoms of helium coalesce into what's called a Bose-Einstein condensate. And that Bose-Einstein condensate no longer has individual atoms. The entire aggregate, no matter how much it is, acts as if it were a singularity, a single atom. And that now we know by 2001 that there are many different kinds of material that can be brought into a Bose-Einstein concentrate, and that it seems to be a universal property of matter that at the extreme of its individuality in terms of time, in terms of space, in terms of structure, at the limit of its extreme, one of the characteristic universal transformations is that it gains the quality of singleness. It gains what we would call traditionally a characteristic of absolute unity. Now, our education in the first year started off with the simplest of developments. We started with Thoreau and with the I Ching, with Thoreau walking in the woods, with Thoreau standing amidst a bunch of trees in the wintertime, saying that he became a part of the grove of the trees in the snowstorm because no one had done that. And that he was there not to observe the trees, but to be with them, to be one with them in a snowstorm, and that he achieved this particular kind of singularity. And we notice that in his journals about the summer of 1840, the beginnings of his vision that this might be possible, and by the winter of 1840, he had achieved this. He achieved the singularity with nature to the extent that he was no longer separable from the trees nor the snowstorm. And we also used the I Ching, where the I Ching some 3,000 years ago talked about how there was indeed a yin and a yang that came together, and when they came together, they formed a deep unity which was called Te, and that Te was distinct from the boundless matrix out of which that unity emerged, and that boundless matrix out of which the Te emerged was given the name Tao. And that while yin yang come together to make Te, Te and Tao are a complementarity that do not make a unity. That the zero-ness of the Tao that allows for the oneness of the Te to emerge never integrate, but instead have a relationship which is different, a whole different mode. Its mode, the relationship between Tao and Te, is the relationship of complementarity. Yin and yang integrate to form a unity, but tau and te don't integrate. They relate proportionately in ratios of complementarity. And so the second year of our education was all about how differentiation with consciousness leads to an appreciation that the actual context in which we live and occur, the actual matrix out of which nature and the whole integral cycle comes, is a differential relationality. The differential relationality to that integral, to that whole integral ecology, to anything in that integral ecology, and that condition is the relationality of a complementarity, and how the two together are not two that become one, but a one and a zero that don't integrate. They make a ratioed quality. That is a context that reiterates itself in the substrate of every integral form and of every differential form. And so we saw in our education, and we're there now towards the end of our education. It's taken us almost 2 years of steady, quiet inquiry, of appreciation, building, subtlety, and nuance, so that we come now to nuclear physics on the level of Niels Bohr, where in the early part of the 20th century, in 1922, he published a little book here from Cambridge University Press in England, The Theory of Spectra and Atomic Constitution. 3 essays, the first essay of which was published just before Christmas 1913. And that little essay published just before Christmas of 1913, before the First World War, Niels Bohr focused on the simplest atom, the one we were talking about, the atom of hydrogen. But he focused on the atom of hydrogen not in the way of existence as an integral thing, as an ultimate constituent of matter, that atoms as the ultimate particle of matter were not the issue. The title of the paper is The Spectrum of Hydrogen. The Spectrum of Hydrogen. And for that, we have to understand and realize that he is speaking here not of the unity of an atom as an integral form, but the spectrum is a differential array of possibility that comes from a transform of that form. So that a spectrum is a transformation of integral form into a differential array of possibility. It's quite interesting. The first person to make a spectrum was about 800 years ago and used pure intuition to understand that when you looked at a rainbow in a clearing sky with the rain still falling in the distance, the person who realized this was an Englishman, and he, in fact, at one point in his career was the Bishop of Lincolnshire. But at the point where he was watching this rainbow, after the rainstorm, still raining off in the distance, he was the head of the then science section of Oxford University in England. His name was Robert Grosseteste. And he wrote a little pamphlet called On Light. And in On Light, 800 years ago, he pointed out to his prize graduate student, Roger Bacon, he said, every drop of water in a rainbow is itself has a rainbow. The drops of water within a rainbow are not the upper ones are green, the lower ones are yellow, and the ones below that blue, but that every drop of water in a rainbow has within itself a complete rainbow. It was an extraordinary statement to make 800 years ago. It was a high point of scientific intuition at a time where they couldn't make much use out of it other than the sense of wonder that, I guess you know that the traditional Jewish use of the symbol of the rainbow is that it was the first seal of the first covenant. In Genesis, the first covenant between Abraham and God is sealed by the rainbow. And so it was understood in the kind of scientific Oxford, medieval, alchemical, Franciscan Christianity of that day as proof that the scriptures were telling the truth, but that man had to dig deeper to understand exactly what that meant. It wasn't until the 1860s, some almost 600 years after it, that a man named Kirchhoff made the first scientific spectrum of an element and saw that it isn't just rainbows coming, diffracting from drops of water with sunlight after a storm, but that all atomic material, all atomic elements have their own spectrum, their own kind of rainbow, and that this can be known. And it took a long time. It took about 25 years for a man to come up with the atomic spectrum of hydrogen. That was done about the same year that Niels Bohr was born, about 1885. When it happened, in 1885, when the spectrum of hydrogen was first really determined in the scientific paper published, it occurred to the most profound mind of that time. The most profound mind of that time was another Englishman named James Clerk Maxwell. And Maxwell was the head of the Cavendish laboratory at Cambridge University in England. That laboratory had been founded earlier in the century, and the first director of the Cavendish was a man, also a great scientist, Lord Rayleigh. The second director was James Clerk Maxwell. And Maxwell noticed that his recently published theory, his theory on the mathematics of the electromagnetic spectrum, tied in with the spectrum of hydrogen in such a way that one could analyze that spectrum, that rainbow of the element hydrogen, and you could come up with a mathematical ratioing of the different components of that rainbow so that you could get the spectral signature of the element hydrogen complete in not just its registry as one element in an array, but that the various steps in the wave forms of that registry could all be separated mathematically, and that one could count. Maxwell at the time went through the top 5 waves of the spectrum of hydrogen. Even though there are other ones, they weren't as necessary. They were just little auxiliary additions. The top 5 waves could be counted mathematically, and that you could come up with an understanding that there was a mathematical spacing in between these waves, and that the element hydrogen wasn't just something that existed as a piece of matter, but also existed as a form of energy frequency, as a wave. it was such an astounding thing that existence not only occurs as things, but at the very same time occurs as energy frequencies. That existence is both particle and wave, not through some kind of conundrum, but through a kind of a yin-yang quality that could be integrated, that could be brought together. And so the search went on to try to find, how do we bring energy and matter together into a mathematical unity so that we could say, or at least write down in the symbol language of mathematics, so that we could say what the unity of existence really was, with matter and energy integrated and brought to a form. And the man who did that was Albert Einstein, 1905. He was able first to say that the whole electromagnetic spectrum itself is carried integrally by a single T, a single particle that carried all of the unity of the entire electromagnetic spectrum within itself, within its form, and that particle was light, was the photon. Now, in 1905, no one could find a photon. It took the better part of about 18 years. A man named Arthur Compton, about 1923, formed some experiments that finally the photon was found as a particle, and Einstein was vindicated. And of course, Einstein, puffing his pipe, and already his hair starting to gray, was already light years beyond where those experiments were. And he was predicting things that only were found at the beginning of the 21st century. But at that time, when the photon was found in 1923, it was the third particle that was found to make up the atomic nature of the world. And that the first particle that had been found had actually been found almost, 27 years before. And that first particle was the electron. And the electron was found by the man who succeeded James Clerk Maxwell as the director of the Cavendish Laboratory. And his name was J.J. Thomson, Joseph John Thomson. J.J. Thomson was never allowed to touch equipment because he had one of those odd, quirky personalities that he broke equipment. Glassware in laboratories would somehow always end up shattered on the floor. And so they told Thomson he was a wonderful director, but that he should wander around to all the experiments and really not do any of them himself. And one of the men who was entrusted, one of the young men who was entrusted with the experiments, because he was very good at instruments and glass, was a young New Zealander named Ernest Rutherford. And so Rutherford, who later succeeded J.J. Thomson as the director of the Cavendish, began to work with experiments. And his experimental equipment, when he first came to England from New Zealand, he liked radio waves. He liked to experiment with radio waves, and he thought, radio waves are the most interesting aspect of the electromagnetic spectrum because you can actually send the human voice via its inclusion into a radio wave frequency, and you could send it at a distance. He actually, way back at the beginning of the 20th century, managed to send his voice 2 miles to the Cambridge Observatory from the Cavendish Laboratory, and people thought it was just pure magic. How can you do this? That you could send a voice through 2 miles, and it would come out, and it would sound just like somebody talking there. But when he got interested in handling the glass around the Cavendish, because they wouldn't let Thomson handle it, Rutherford suddenly, because he was like a dogged kind of an individual, he not only needed to know, he needed to find other people who would believe that they needed to know as well. And so he became very good at encouraging graduate students to do the kind of research that he was interested in. And he got interested in radioactivity because it occurred to him that what was happening in radioactivity had something to do with the electrons that Thomson had found, had discovered, the negative charges of energy that were around, and that somehow radioactivity was related to the electrons in such a way that he wasn't sure just what it was. He was acquainted with Einstein's theory of the photon, but he was not very good at theory. And so Rutherford concentrated on what is it that allows for radioactivity from an atom, certain atoms, complex atoms like uranium or like radium, to send out radioactivity. And just what was radioactivity? And the world's first book on radioactivity came out in 1904 by Rutherford, published by Cambridge. And within a few years, Rutherford had found that so much more was knowable so quickly that this 1913 edition is no longer just called Radioactivity, but is entitled Radioactive Substances and Their Radiations. And it's about 600 pages. And chapter 4 is on the alpha rays, because by this time, Rutherford, who was very dogged, he had left Cambridge, and he had actually gone over to Canada. He went to Quebec. He went to McGill University in Montreal. And while he was there for about 9 years, McGill became the place in the world that you went if you wanted to find out the actualities, the ins and outs, through experiment, not through theory, but through experiment. You went to study with Rutherford because he was the man who was making the equipment and the experiments, because he was convinced that there must be something there, not just mathematically, but that the universe really does exist. It is a material, and so there must be something there that works with the electron. And he was so successful that finally Manchester University hired him away from McGill. He went back to England from Canada, and by 1911, by about March of 1911, one of his graduate students noticed that there was a particular kind of an influence on photographic plates that was different at different times. That obviously, whatever radiation was, there were several varieties of it. And so by late 1911, early 1912, Rutherford found that there are actually 3 types of radiation. He called them alpha, beta, and gamma. He said there are alpha rays, there are beta waves, and there are gamma waves. And that the alpha rays are very readily absorbed by thin metal foil and by a few centimeters of air, so that matter absorbs radiation. And when it absorbs radiation to an extent where it is completely full, where it is saturated, that radiation then is re-emitted as an emission, so that matter absorbs and emits radiation. Einstein had said that matter also absorbs and emits light. that light energy can be absorbed by matter, it can be radiated. And so Rutherford knew that he was on the track of something major here. The beta rays are, he writes, on average far more penetrating in character than the alpha rays. The alpha rays go just a few centimeters of air and just into thin foil, but the beta rays consist of negatively charged bodies projected with velocities on the same order as the velocity of light. That beta radiation has the same velocity as light, and they are more readily deflected than the alpha rays and are of a type identical with the cathode rays produced in a vacuum tube. And of course, this eventually led to the development of television. The third kind of radiation was gamma rays, and he says the gamma rays are extremely penetrating and non-deviable by either a magnetic or electric field, and their true nature is not definitely settled, but they are analogous in most respects to those very penetrating rays found by a German experimenter named Röntgen. So that gamma rays, very similar to X-rays. And we know now that on a cosmic level, gamma rays and X-rays occur because of neutron stars, because of black holes, because of exploding stars called nova or supernova, and that these saturate all of the galactic structures and in between in all of the known universe. What was interesting to Rutherford was that all of this had to have, because of his New Zealander quality of sticking to the basics, he knew there must be then a particle which holds a relationship with the electrons and which has something to do with the structure of the atom and has something to do with the way in which radiation happens. And by 1912, by the time he was writing this version of his book, he had found the proton. As soon as Rutherford found the proton, he found it not by theory, but because he had patiently, like a bulldog, had amassed the experimental investigations. He had amassed the leaves of all the reports into a flower of not so much discovery, but of disclosure. So that you had on one hand an Einstein who was a theoretical genius, and on the other hand you had experimental geniuses like Thomson, like Rutherford, and what you needed at that point was somebody who could bridge in between the two realms, and that person was Niels Bohr. He was able to follow within his mind the contemplative vision of theory and yet interface it effortlessly to his attention to the experimental side. Not so much the inner theory with the outer practice, but the interface between the two of them was such that, as Bohr put it in one of his writings later in life, he said it's not just so much that there's an integration of inner mind with outer experiment. It's that the mind itself changes and that the outer materia also changes. And they tend to become not one thing, but they tend to become a complementarity. And so Bohr is one of the great figures in world history. Not just someone who bridges inner and outer, not someone who just makes an integration, and not someone who theoretically, like an Einstein, can appreciate the differential complexities, but Bohr is someone who is magisterial in that he saw that the differential and integral together do not make another integral on a higher order, but make a complementarity that has within it a transform of both. That not only does matter change its form, but that the mind changes its form as well. Let's take a break. What Niels Bohr began to realize was that his mind was transforming and beginning to keep pace with the transformations of material in the experiments. It's a remarkable thing. Not just that matter transforms, but that matter transforms exactly in correspondence to the way that the mind is able to transform mathematically. That the equations were not descriptive, but that the equations corresponded to the experiments in such an exacting pairedness, a symmetry, actually, that there were times when the experiments took a predictive lead and the math then had to discover its correspondence, or on the other hand, that the math would take a predictive lead and the experiments would have to catch up. And it was like a shadow play where the actual physical experiments began to interpenetrate with and weave with the mind's theoretical capacity to do the math. It occurred to someone as staid as Ernest Rutherford, who was as solid and staid a British Empire citizen as you would ever want to have. He began to understand that this was a magical relationship. His last book, in 1936, he was one of the most honored physicists in the world, was called The Newer Alchemy. Bohr, when he gave in 1932, he gave a lecture, the Faraday Lecture, in honor of wonderful Michael Faraday, who had been an early 19th century physicist. We've talked about Faraday before. He was literally an ordinary man off the street. And because of his curiosity, he was welcomed into Sir Humphrey Davy's laboratory, literally to sweep floors to begin with. And eventually Faraday became one of the world's great physicists. He ended up lecturing in London every Friday night, and he always let anyone off the street come into his lectures because that's where he came from. The Faraday Lecture of 1932, given to those there in London at the Institute, published in the Journal of Chemical Society, is called Chemistry and Quantum Theory of Atomic Constitution. And he talks about a deep reverence to be able to give a lecture here, the podium where Michael Faraday had given lectures, and that it was in fact Faraday's work that led to Maxwell's theories of the electromagnetic spectrum and structure, that led to Einstein, that led to all the development of nuclear physics. It is a tribute, he says, to be able to be here where this man was, and that at this particular time, I speak to you as an atomic physicist and you as chemists, and the dividing wall between us no longer holds, because we have come to such a deep understanding of structure that the divisions between the different sciences are not only disappearing, but that they were artifacts of ignorance in the first place. They were never there. And it would only be 3 years later that a brilliant young Linus Pauling would write the world's first textbook on quantum chemistry. Bohr says in here, certainly Faraday's work may be taken as a symbol of that intimate relationship of our sciences, chemistry and physics, between which all sharp distinction is now disappearing on account of the rapid growth of our insight. On account of the rapid growth of our insight, that our visionary consciousness is penetrating, and as it penetrates through the structure of the outer world on the subatomic level, it recursively penetrates through the symbolic forms, the integral ideas that were like atoms of thought, and that we are at the same time, when we are aware, we are concomitantly maturing together. It's not just that we are mentally understanding the universe in a deeper, integral way, but that we are changing the possibilities of the universe in its integral structure through our ability to add a dimension of consciousness, to add a transform of analysis, so that we not only look with new eyes, what we see is new also. And that the largely invisible orders of the universe have joined the spectrum of possibility, so that what was the rainbow before now is expanded many millions of times. We talked about Robert Grosseteste looking at the rainbow 800 years ago, writing the little medieval classic book on light. Every raindrop within a rainbow is itself a rainbow. And that same principle used in the 19th century and the late 1860s by Boltzmann, when he realized that the viscosity of gas, the atoms that make up a gas, was independent of its density, and how puzzling that was to James Clerk Maxwell, that it went against common sense, but that as you understood, that there was an atomic nature to viscosity. The less dense, the faster something would go through a cloud of gas, and it would encounter the same number of atoms of gas. And that insight led to the understanding that there was not just an array of individuality in the universe integrally, but that there was such a thing as a distributed, averaging, a statistical emergence of characteristic vector of action. It's sometimes called the bell curve. The scientist who first developed that was named Gauss. The bell curve of statistical probability applies consistently and even to the billions of atoms in a cloud of gas their movement is all really individual, atom by atom, but there is such a thing as a bell curve statistical averaging norm, and the gas itself will act as if it were averaged out, and yet there is an extreme of integration where the gas acts as a Bose-Einstein condensate, acts as a singularity. That nature, no matter what else she is, does not provide ever dead ends. Nature never comes at any time, anywhere, to a dead end. That the so-called limits, the so-called boundaries, are, as they are approached closer and closer, they more and more become thresholds of transform rather than stops. And that if you could tune into the language of nature's mystery, it is a non-stopped, non-punctuated song. In the classical Byzantine Orthodox form of Christianity, it's called prayer without end. It is a quality in Buddhist meditation called ekagrata, one-pointedness of mind, and that one-pointedness of mind is not brittle, nor is it a period. It doesn't stop, but what it does is vanish. And that the vanishment of the single-pointedness of mind discloses the context without boundary that allowed for the emergence of ekagrata in the first place. That Tao cannot be counted, but always occurs and is especially evident when Te emerges as a unity. And that the disappearance of an integral means that you have begun a differential. And that they form not only a complementarity, but that their realms form a correspondence. So that in another lecture by Bohr later on, in his lecture on atomic theory and mechanics, 1925, he writes about the correspondence principle. And he writes in terms that we can now appreciate, given this morning's part of the lecture, given our attention, given our 8 lectures on science, given our 2 years of education. We're in a sensitized position to be able to read with Bohr as his pen writes and says, nevertheless, it has been possible to construct mechanical pictures of the stationary states which rest on the concept of the nuclear atom and have been essential in interpreting the specific properties of the elements. He's saying with all this dynamic, with this array of incredible boundless possibilities, nevertheless, within that, matter does exist stably, holds its forms, but that the holding of its forms are not happenstance. They're exacting, and they occur especially not in terms of poundability of matter, but they're stable because of the interlock of oscillating frequencies of electricity and magnetism that hold at specific energy levels. That electrons hold at a specific energy level. And they don't hold at any other energy level anywhere in the universe, in any star system, in any galactic structure. This is the energy level of the electron. And if you go to put an actual number on this, a figure on this, one can come out exactly with the numbers. But the difficulty that was found measuring the electron's energy, any electron's energy, at 0.511 megavolts, that energy, though it's very high in terms of such a small thing as the atom, and we talked this morning about how if the atom were expanded to the size of a football field, the proton of a hydrogen atom would be a marble on the 50-yard line. And that all of the rest of that football field is kept into solidity, kept into the power of existence as a hydrogen atom by the relationship of that little piece of negative energy, the electron, vis-a-vis that marble proton. And it was discovered later, about 60 years after Bohr writing this on the correspondence principle. It was discovered that the electron, that bit of negative charge, which somehow must respond to the same universe where light, the particle of the photon, carries electromagnetic energy, the electron carries electric energy. And that its relationship with the center of the atom, with the proton, is one of a stable, balanced, electrical plus and minus coming together. And that, in fact, the electron, while it exists exactly always at 0.511 megavolts of energy, it has a higher form that wasn't found until 1947, the muon. That the muon is an electron that is energized to such an extent that you don't measure it in just 1 megavolt, but you have to measure it in 105.6 megavolts. That this form, this natural transform of the electron also occurs all over the universe. And about 30 years after that, it was found that there is, in fact, a third energy level, that the electron raised to the muon is a huge jump. It's over 210 times more energized, more powerful. But that the third state of the electron, the tau is measured in gigavolts, not megavolts. 1,784 gigavolts. And that the electron, when it is raised to the level of the tau, that you begin to get a blurring of the possibilities of protons and neutrons being able to handle the relationship. And so you go into a transformed spectrum of matter. And this, of course, is where experiment is carried on now in the early 21st century. Well, let's come back to Bohr, back to 1925, back to the correspondence principle, not a metaphysics. Not a metaphysics at all. He says, in the simplest case, like hydrogen, of an atom with only one electron, such as the neutral hydrogen atom, the orbit of the electron would be, in classical mechanics, a closed ellipse, obeying Kepler's laws, just like a planet going around a sun. it would always have an elliptical form to its orbit, and the math existed at that time, even in 1925, even in 1725, even in 1625. The math existed to compute the properties of the whole ellipse, according to which the major axis and frequency of revolution are connected in a simple way. The major axis and the frequency of revolution connected in a simple way with the work necessary for a complete separation of the atomic particles. Now, if we regard the spectral terms of the hydrogen spectrum as determining this work, we see that in that spectrum evidence of the step-like process through which the electron, under emission of radiation, is gradually bound more and more firmly in states visualized as orbits of smaller and smaller dimensions, when the electron is bound as firmly as possible, and the atom can therefore emit no further radiation. That is, as energy is emitted as radiation, the electron's orbit becomes smaller and smaller, closer and closer to the proton. When the electron is bound as firmly as possible and the atom can therefore emit no further radiation, the normal state of the atom has been reached. The orbital dimensions estimated from the spectral terms have values for this state of the same order of magnitude as the atomic dimensions obtained from the mechanical properties of the elements. From the nature of the postulates, however, such features of the mechanical pictures as frequency of revolution and shape of the electronic orbits are not open to comparison with the actual observations. The symbolic character of these pictures can scarcely be more strongly emphasized than by the fact that in the normal state, no radiation is emitted. Normal hydrogen doesn't emit radiation. Normal elements don't emit radiation. All matter would become radioactive in a short amount of time. But it can scarcely be emphasized stronger than by the fact that in the normal state, though no radiation is emitted, although according to the mechanical picture, the electron is still moving. Nevertheless, the visualization of the stationary states by mechanical pictures has brought to light a far-reaching analogy between the quantum theory and the mechanical theory. This analogy was traced by investigating the conditions in the initial stages of the binding process described, where the motions corresponding to successive stationary states differ comparatively little with each other. Here it was possible to demonstrate an asymptotic agreement between spectrum and motion. This agreement establishes a quantitative relation by which the constant appearing in the formula, the original formula in 1885 for the spectrum of hydrogen, a man named Balmer. For Balmer's formula for the hydrogen spectrum is expressed in terms of Planck's constant. In 1900, Max Planck had discovered that there is a universal constant. He designated it as H. And there's a little bit of a slash on the top of the H when you use it in a quantum mechanical way for that mathematical symbol. What he is talking about here is that there's a very curious thing when one looks at the spectrum of hydrogen. It's not just that there is a spectrum of this element, but that that spectrum exists by having a whole series of lines, like the waves that add up to a kind of a disturbance someplace out on the ocean. There'll be a whole series of waves. You've heard the saying there are 9 waves that come in a tidal wave. and that the fifth wave is the largest. The same in the sense of looking at a spectrum. What makes the lines distinct is that in between them are dark spots, dark lines, areas where there is no registry of energy. That all spectrums contain not only the bright lines of emission, but contain the dark lines where nothing is registering. So that the spectral analysis of anything shows the ones and the zeros at the same time. And that one could not read this accurately if you didn't work with the binary differential focus of your analytical capacity. You wouldn't even see a spectrum in the first place. You would just see the rainbow with visible light. Kirchhoff's spectrum for material, or Balmer's spectrum for hydrogen, any kind of spectrographical analysis now is all due to a differential consciousness raised to the level of scientific form. And that scientific form is differential form, analytical, and not existential form, integral. Though the differential form can be brought into montage with the integral forms, in which case one can go inside the structure of existential forms and can even go inside the structure of symbolic forms of the mind. This shows a very catastrophic kind of realization that a mind trained purely in natural ecologies of integration, where the reference of the mind are to existential physical things, is a mind that is unable to see in any kind of visionary conscious way. Whatever little smidgen of consciousness there is fully brought back, packaged, ensconced into ritual, brought back and fed and rewoven back into a mythic level of meaning in which there is no history, and interiorized and integrated in terms of ideation, in terms of the mind's symbolic powers, and what you have are very detailed amulets that protect, supposedly, the incursion of any kind of change, any kind of questioning onto the veracity of those forms. So it became apparent by the 1920s to these kinds of individuals working with this kind of realm that they had to let go of the traditional education, the traditional way of learning, at least temporarily, completely. Bohr was famous by saying, if you have a mental picture of something in quantum mechanics, you're lying to yourself. There are no pictures. It isn't that you have the wrong picture. There are no pictures. There are no mythic images. There is no imagery for it. In fact, the traditional mathematics was so limited that it was unable to function. So that by the time, this is from 1964, this is already a third of a century ago, textbooks on relativistic quantum mechanics by two professors at the Stanford Linear Accelerator, their math doesn't look at all like the math that you would find in any kind of text before that. These are Feynman diagrams. Because you had to make up a whole different kind of mathematical language that could interface with the non-image analytical differential forms and processes, and interface with the actual integral forms and integration processes that you find in our ordinary experience, in our existential referent world, in our traditional causal classical mentality. But that if you tried to make sense out of it in terms of reducing everything back so that it was comfortable, so that you understood it in this old mind, in this old experience, in this old poundable world, you are now participating in a delusion. And this, of course, produced an enormous discontinuity, which the general public is just beginning to understand. As one of Roger Penrose's book is called, The Emperor's New Mind. It's rather like letting a genie out of a bottle. You can't coax the genie back into the bottle. It's not going to go. Won't go because can't go. Because once that kind of genie is out of the bottle no longer occurs. There is no bottle for the genie to go back into at all. And that genie is consciousness. There is no way to jam consciousness, once it is freed, back into some stoppered form, no matter how convenient, no matter how supposedly powerful, no matter how supposedly metaphysically sacred, because all of that now amounts to a delusion. Though it may have been satisfactorily true before, it is now impossibly untrue forever. This is a difficult part of the early 21st century. And the difficult part is that if you try to force the future back into a more comfortable present, it turns into a regressed past. And it turns into a regressed past very, very quickly. It isn't that you just regress a few minutes or that you regress a year or so. In 1 year of the 21st century, we have politically regressed 1,000 years. If we keep up the pace, we will be back at the time of Augustus Caesar by the end of 2002. And if we keep it up and are determined, we can get back to the Neolithic by the middle of the first decade of the 21st century. And if we keep it up, we can regress all the way back. There's plenty of time, and there's 70 million years of primate history available for regression, and beyond that are the trilobites that went on for 500 million years. And we can probably make it regressively through most of the 22nd century. But when we get back to the rocks are going to reject us because the geology knows that we are not kosher minerals. We're coming back because the regression always carries a radioactivity with it. That's the nature of the universe. Regression is radioactive. And it doesn't take long for the physiological system. We're very sensitive. We come out of a context that's at least 15 billion years old. Every element in our body has been made in star systems that have long since disappeared. And we're very cosmic, and our bodies are sensitive enough to know that this is a radioactivity that destroys because it corrodes. And the first thing that it corrodes is the top of the integral order. The first thing that corrodes are the higher capacities of the mind. And people will become idiots long before we get through the first decade of the 21st century. No one will understand anything. stay tuned if you think that's an impossibility. What is beautiful about our approach to this is that there are hundreds of millions of people alive now who understand, though they cannot tell you the math, they understand in their lives that there is such a thing as a conscious time-space, a five-dimensional continuum that doesn't just make a context of integration, doesn't just make forms that are there and stay there in certainty, but that a five-dimensional conscious time-space also includes visionary opening up of possibilities. And that material, more and more, is becoming transportable through the membranes of limitation. Modern materials, that is to say contemporary materials, that is to say new conscious time-space materials, are available for possibilities beyond limit. And we take our cue here, as Niels Bohr says over and over again in his writings, we take our cue from Mother Nature. Because not only do electrons occur in three energized varieties, even hydrogen occurs in three energized varieties. You can have a one-proton hydrogen, and then you can add a neutron to that, and you get a neutron and a proton as the nucleus for a hydrogen atom, and it becomes deuterium. It becomes heavy water. And you can add two neutrons to that proton, and it becomes an even more exotic form of hydrogen called tritium. That's what they use in hydrogen bombs. And if you take a tritium nucleus of hydrogen and you add one more proton, the hydrogen becomes helium. And when they first noticed, when Rutherford was first showing the young student Bohr the alpha radiation, the alpha rays, it was realized that what alpha rays were the nuclei of helium that had somehow been freed and manufactured through a process of decay, and that radioactivity was a natural radiation that showed that there was a decay of energy levels. And that eventually, if you let all matter decay, it will all decay down to protons. It will take more zeros of years than anyone cares to write out. But that would be the final state of the material universe, were it just on some kind of pachinko game probability. But the actual fact is that in adding a conscious dimension to space-time, the universe opens into more and more arrays of possibility, and the build-up into complexity becomes asymptotic, goes off the graph. So that instead of there being like a reductive process, consciousness more than makes up for the natural decay of matter. And what we have is an increasingly beautiful array of possibility in the cosmos. It's not so much that we are staggered by the new realms, is that we are overcome by an unaccustomed sense of wonder. And getting acclimated to that unbounded sense of wonder is what an education like this is all about. Sensitizing us to accept and to participate with the wonder world of the real cosmos. The title today is Helical Arcs, Not Old Angles. As long as education was based on geometricity, you had dark corners and you had sharp angles. With this new education, all those angles are just possibilities all within a single arc of boundless helical possibilities of cooperation. The oscillations of electricity and of magnetism blend together and go together indefinitely, and out of the nodes of that cooperation comes the phantom rain of atoms of all the elements. We live in a magical snowstorm of possibility. What we're doing now in this kind of an education is learning to navigate, growing our wings back, as Plotinus once said, so that we can fly free. And like Thoreau, we'll find that no one has ever surveyed this particular forest in this particular kind of snowstorm before, and that we're wonderfully privileged to be able to do so now. More next week.